In the last lecture, we studied the normal vectors of surface in Euclidean space. Suppose a surface S in Rn, the equation of this surface is f, maybe capital F, x0. That is, S is the zero set of a smooth function capital F. Then we know that the normal vector of S at a point P in S is precisely the gradient of capital F at the point P. Okay, this problem is solved in this way. This is S, and this is our point P. So we take a curve minus epsilon gamma 0 is P. This is a curve. The image of this gamma contained in S. This curve is a curve passing P and contained in S. So the trajectory of this curve is a curve in S. Then the tangent vector of this curve gamma at the point P is gamma 0. Therefore, the normal vector by the chain law we know that d dt capital F at t equal to 0 at the point P, gamma t, this is 0. Because gamma t lies in S, therefore f gamma t is 0 for all t, so the derivative is 0. But by the chain law, this is the gradient of capital F at P inner product with the tangent vector of the curve at the point P. So this means all such tangent vectors are contained in a plane perpendicular to the gradient of capital F. So this plane is called a tangent plane, and the gradient of capital F at the point P is the normal vector of the tangent plane. We call this the normal vector of the surface S at the point P. Okay, and we also study the case in three-dimensional case. In R3, a surface S can also be expressed by parametric equation. That is, x is xuv, y is yuv, z is zuv. So this is a uv plane, and here we have a point AB. Okay, so this point is mapped into the surface. The map is phi. That is to say, phi uv is x uv, y uv, z uv, and at the point AB, the point AB is mapped to the point P on the surface. Phi AB is P in the surface. Then the method is that we fix the V, but let U change. So this map U is mapped into phi UB. We set V always to be B. That is, we restrict the point UV one line on a segment passing through the point AB and parallel to the U axis. Then this segment is mapped by the map phi to a curve on the surface passing through the point P. So the tangent vector is the derivative at the point u equal to a. So tangent is the derivative of phi at the point the derivative of this map at the point u equal to a. Okay, that is the partial derivative of phi with respect to u at the point AB. At the point AB. Similarly, we consider another map v map to phi a v. Then the tangent vector of this map is dv phi ab. So these two vectors are tangent vectors of transversal curves passing through P on the surface. So this is dv phi. This one is dv. This one is du phi. Okay, so they are cross product. Their cross product is perpendicular to both vectors. Therefore, geometrically, this should be the normal vector of our surface. Okay. So by direct computation, you see that this n equals yz, the Jacobian determinant of yz with respect to uv, then jx with respect to uv, and xy with respect to uv. So this is the formula to compute the normal vectors of a surface given by parametric equations. Okay. Now this is in R3, three-dimensional. A natural question is, can we deal with the higher dimensional surface? For example, in R6, a surface with 5 parameters in R6, 6-dimensional Euclidean space. How to compute the normal vector of such a higher dimensional surface or hypersurface? So the method we applied for the 3-dimensional case is not applicable, because in 3 dimension we have a cross product. We use the cross product here to get our result. The cross product is not available in higher dimensional space, so we need to find another method to solve this problem. Okay, we start this for today's lecture. Now, suppose capital U is an open subset of Rn-1, and a point A in U, and a map phi from U to n-dimensional space is C1, and satisfies another condition. The derivative of this map at the point A, phi point A, this is an n by n-1 matrix. Okay, because U is n-1 dimensional and Rn is n-dimensional, so the derivative of this phi at the point A is an n by n-1 matrix. The rank of this matrix, a metric you can, if it is a square metric, you can take determinant. But if this is not a square metric, you could not take determinant, but you can compute the rank of the matrix. That is the largest number of the linearly independent column vectors. This is also equal to the largest number of the linearly independent row vectors. Okay, and also this is the highest order of the non-zero determinant contained in this matrix. We assume that this matrix, the rank of this matrix is n-1. This is a regular assumption, regularity assumption. Regular. If the rank is less than n-1, the image of this phi will be very strange and could not be called a surface. Only when the rank is n-1, that is the largest rank, because this is an n by n-1 matrix. The rank of this matrix at most n-1. Now we assume that it is exactly n-1. Okay, so in this case we say that the S, the image of this map is a surface in Rn. Of course, this surface, the phi is the parametrization of this surface, and because there are n-1 parameters, so this S has n-1. The number of freedom of this S is n-1. So we sometimes call this n-1 dimensional surface or hypersurface, or we can say the codimension is 1. Codimension equal to 1, maybe. Okay, so in the case n equal to 3, this is exactly the our usual surface in 3-dimensional space. But now we consider higher dimensional case. Okay, so assume that P is phi A, the image of A. So this is U, this is A, and this is phi, and this is our S. S is the image of our map phi, and the P is the point corresponding to A. P is a point in the surface. So we want to find the normal vector of this surface S, higher dimensional surface at the point P. We want to find the normal vector. Okay, so how to find the normal vector? The cross product we use in 3-dimensional is not applicable here. Now we take the following approach. Okay, for any h in n-1 dimension, that is, we fix a direction h and consider the line passing through A and in the direction of h. So this is this direction is h. So this is the line passing through A. Okay, so this line, the part of this line containing in the set U is mapped by the phi, by our map phi into the surface, become a curve on the surface passing through P, because phi A is P. Okay, so we get a curve passing through P. This is the curve, and the tangent vector of this curve. This curve is phi A plus th. For t small, for t very small. This curve, this map describe a curve on S passing through P. So this is a curve on S through P, passing P, our point P. Okay, now the tangent vector of this curve, the tangent vector, this curve is denoted by gamma. Okay, so the tangent vector is of this curve at the point P is the derivative at 0 is okay, because the point P corresponding to t equal to 0. So the tangent vector is the derivative of this curve, this map gamma at the point t equal to 0. This is the determinant of at t equal to 0 phi A plus th. And by the chain law, this is the phi prime A and the h. Phi prime A is an n-1 matrix, and h is an n-1 dimensional column vector. Therefore, the result of this multiplication is an n-dimensional vector. That is gamma 0. That is the tangent vector of this red curve on the surface. Okay.